All right, everybody, this is our last lesson in Chapter 13, Redox Stoich, and our last new information before spring break. Yay, happy news. Okay, today's lesson is a little long. I'm going to apologize for that. It's just a lot of stuff to cover, and the examples take quite a while to go through. I'm also going to apologize because I couldn't find any good demonstrations or videos on this. I found one reasonable one that shows you what these redox titrations look like, and that was it. So lots of theory and a little bit of math. You will want to have your data book with you, open to page number 7. You'll need those half reactions from the table of relative strengths. You'll also need your calculator for the stoichiometry, and we are working on page 212 in your study guide to follow along. So just a reminder, we're doing solution stoichiometry, and in solution stoich, you are always starting with the moles per liter times the liters, which is going to give you the moles of one of the two chemicals. So let's call it chemical X. So you're going to get the moles. That's not a good choice. Let's put it here. Moles per liter of chemical Z. So you're going to get the moles of Z. And then you're going to use a molar ratio from the balanced equation, and you're going to put the chemical you're looking for on top. Let's say in our balanced equation, 3Y are produced for every 1 Z. That's going to give you your moles of chemical Y, and then you're going to divide by the volume of chemical Y to get the moles per liter of chemical Y. So that's sort of our standard pattern for these solution stoich problems. And I'll review that as we go through it. Redox stoichiometry has tons of practical applications. There's a section listed here. It's used in industry. It's used in monitoring for quantities of chemicals and all kinds of reactions. Hospital labs, the mining industry uses this to try and measure the concentration of metal ions before they decide whether or not to spend millions of dollars mining for those metal ions in rock and soil. So lots of uses. Lots of this determines whether or not applications are profitable. So very valuable, very practical. Lab techs do these titrations every day. All right, so the theory behind these, how do these things work? So just to review, when you do acid-base titrations, you're always titrating an acid with a base. One of the two is your unknown, and the unknown is its concentration. So you're trying to find out concentration of one of the two. Same thing with redox. The big difference is that in redox titrations, you don't have to add any indicators because the indicators are the oxidizing agents. So there are two strong oxidizing agents that act as indicators. In other words, they change color when they gain electrons and become reduced. So we have two oxidizing agents that do this really well. So they are used in redox titrations, and we use those strong oxidizing agents to react with reducing agents, and that allows us to find out the concentration of the reducing agents. Okay, so what are they? Acidified permanganate ions and acidified dichromate ions. They're both colorful and they're both strong oxidizing agents when acidic. So permanganate is purple in its when it's acidified, it's purple. It's purple anyway, but in an acidic solution, it can gain electrons and then switch to its colorless form. And I put it as pale pink because usually what happens is it turns colorless, and then you always add one extra drop of this guy, and then you get a very pale pink color when you're done the titration and you stop. The second one that we don't use in the high school lab because it's toxic is acidified dichromate. And dichromate reacts with reducing agents, and it gains electrons. So it is an oxidizing agent. It gains electrons and becomes reduced to chromium-3 ions, which are green in color. And this 7 water should be sitting over here as that half reaction. Okay, so In this titration, orange becomes green, and in this titration, purple becomes a very pale pink. So what would these look like in the lab? Okay, well, in the lab, you would have your reducing agent in your Erlenmeyer flask, and you would have your strong oxidizing agent in the burette, in this case the purple permanganate, and you would add it drop by drop. It would react with the reducing agent and turn colorless. It would stay colorless until the reaction is complete. And when it's complete, you'll add one more drop, and that drop of purple will dilute in the water and make pink. And as soon as you see pink, you stop. For the dichromate titration, the orange turns to green as it gets reduced. When it's done being reduced, your next drop of orange stays orange, and you would stop again at the orange color. So our strong oxidizing agent is gaining electrons and becomes reduced, forming a different color. Once that reaction is done, you stay at your original color. Okay, I am going to jump to the data book and just show you these two reactions on a table of relative strengths on page 7. So here they are. Permanganate, acidified permanganate, is the third strongest oxidizing agent, and acidified dichromate is the 8th strongest. So these are both very strong oxidizing agents. They will react with pretty much every reducing agent in the table, especially permanganate. These are the only two that it won't react with. So this is the most useful oxidizing agent for redox titrations. It can be used to find out the concentration of any one of these reducing agents down the entire table. And in industry, it's useful. Well, it's just got tons of uses. We'll leave it at that. Okay. Some more theory for you. So redox titrations, what makes them a little harder than acid-base is there's two separate sets of titrations. The reason for this is when you start with your acidified permanganate or acidified dichromate, they're such strong oxidizing agents that they will even spontaneously react with water. Here's water. So both of them can spontaneously react with the water that they're dissolved in because they're aqueous solutions. So your concentration can change. So if I ask the lab tech to make 0.150 moles per liter, by the time I get it out into the lab, it might be 0.148, but I don't know that. So the first step in a redox titration is to standardize or determine the concentration of your strong oxidizing agent with a primary standard. Now, you might remember that's from Chem 20. You had to build primary standards where you take an exact mass and you dissolve it in an exact volume in a volumetric flask, and then you fill it up to exactly 100 milliliters, and that's your primary standard. And then you can pipette 10 mil samples from that, and that was your first part of the titration. So that's what you're doing with these redox. You're making a primary standard of an exact known concentration, and then you're titrating it with your acidified potassium permanganate or acidified dichromate to figure out its concentration. So that's like step 1 or part 1. Then you move on to step 2. Now that you know this concentration, so we would say concentration known, then you can do the second part of the reaction. So to summarize down here, 2 parts to the titration. Part 1 is standardization of your strong oxidizing agent using your primary standard. And then part 2 is determining the concentration of your reducing agent using the strong oxidizing agent from part 1. And you now know its concentration to allow you to do that. So I know that's a little confusing, So let's take a break and watch a short video. What does this titration look like? So we're going to do this one with the purple acidified potassium permanganate. And it's in this example, I believe it's reacting with iron 2 plus. Okay, so this would be your iron 2 plus in the Erlenmeyer flask. It's acidified. We're adding the permanganate. It's reacting. It's an oxidizing agent gaining electrons and becoming colorless. So every drop, the purple disappears until the purple is completely, or the oxidizing agent has used up all the reducing agent, and then you stop. You get your final volume of your permanganate, and then you can do the titration. So just to show you that again, the permanganate is reacting with the reducing agent in the volumetric flask. Once all the reducing agent is used up, then the permanganate no longer reacts. It stays purple, and that purple drop in your colorless solution leaves you with pink. And so you stop at pink, which is what this is saying. Stop when you get one drop of purple dissolved in there, giving you your pink color. And we say the reaction is complete. Okay, in visual form, part 1, standardization of the strong oxidizing agent. In other words, you're figuring out its concentration. So up here, we would say concentration is unknown at the start. This is your primary standard, which you built. So we say that its concentration is known. And usually it's 10 mil samples. Once this is done, now we've figured out this concentration. We do stoich. So now its concentration is known. It's the same strong oxidizing agent. And now we have a new reducing agent. Whoops. And its concentration is unknown. So this is the goal of the lab. Figure out the concentration of a reducing agent. And before you get there, of course, you got to do this step first in order to find out this guy. Bring it over here, and then you can find out this one. So it's a little tricky. If we did this out in the lab, it takes an entire lab period. It's quite stressful, quite challenging. It's right up there with the aspirin titration lab that you did in Chem 20. Okay, so now we'll get into the math, the stoichiometry of this. So you have to be good at writing balanced redox reactions because you need a balanced chemical equation in order to do the stoichiometry. Okay, let's take a look at this. So usually you're given a titration chart like this, and the title gives you most of the information that you need. So if you look at this title, we have 10 milliliters of that concentration of Fe2+. So if I did a little diagram off to the side, I would have 10 milliliters of Fe2+, and we know its concentration. And we are titrating into that Cr2O72-, and it's going to be acidified, and we usually add the acid into here, but as soon as the drops land, they're acidified and they can react. So I'm just going to put H+ there. So in this one, there's our dichromate, our strong oxidizing agent, and this is the primary standard that we built, so we know its exact concentration. Okay, to do the stoich, we need a balanced chemical equation. So here's our strong oxidizing agent. Iron 2+ is our reducing agent if you look it up in the table of relative strengths. Iron 2+, oh, this is a mess. Okay, reducing agents, so we're in this column. Oh, there it is right there. So here it is as a reducing agent. It loses one electron and becomes iron 3+. Loses one electron and becomes iron 3+. Okay, we need a balanced redox reaction. 6 gained and 1 lost. So we got to multiply everything by 6. Okay, electrons cancel out. 1 dichromate with 14 acidic ions, 6 iron 2 plus, gives us 6 iron 3 plus, 2 dichromate, and 7 water. Okay, so we got our balanced equation. Now we need to do the stoichiometry. And as I said at the start, you always do your stoich with the concentration and volume of the chemical you know. Whoops. And we are looking for what is the concentration of the potassium dichromate solution. Okay, so concentration of the Cr2O7, if I put potassium dichromate, it's K2. Concentration of K2Cr2O7 or Cr2O7 2 minus. Okay, start with the concentration and the volume of the chemical we know. So we are given the volume and concentration of iron 2 plus. 0.0500 moles per liter of iron 2 plus times its volume, 10 mil. Okay, that gives me my moles. Perfect. Moles of iron 2 plus. We're looking for dichromate, so we go up to our balanced equation. 1 dichromate ion reacts for every 6 Fe2 plus. So remember, you're always putting the ion, you want to cancel out on the bottom. So now I've got the moles of dichromate, and I want concentration, so I need moles per liter. Where do I get the liters of dichromate? From the table. So we are titrating this with dichromate, and we have all these volumes. So the first titration, we started at 13.8 and we finished at 2.3. So what volume did we use? 11.5. Okay, and you remember from acid-base titrations, you get all your volumes. So this one is 10.6, 10.8, and 10.7. I hope I did that right. So a 10, this one gets tossed. It's a ballpark. These are our 3 that are all within 0.1 of each other. So we're going to divide that by 3 and get the average, which will be 10.7 mil. Okay, so that is the volume of Cr2O7 2 minus. So we used 10.7 milliliters of that as an average volume, 10.7 milliliters. If you're paying attention to units, the milliliters cancel out, the irons cancel out, and we are left with moles per liter of dichromate. When you do the math, you get 0.07788 moles per liter, and there it is with the correct sig digs. So that's part 1 of the titration. I'm just going to go back to this slide. So we just figured out this concentration using a primary standard where we knew its concentration, we knew its volume, we did the stoich, and now we know this. So we can bring that forward to titration number 2. So we're going to take this value and bring it forward to titration number 2. So there it is. Whoa, was that to the 3 or to the 2? That is to the -3. Okay, I wrote that out wrong. Casey would have caught that. 0.0077788 moles per liter. Okay. So now in part 2, we've now got the concentration of our dichromate, or our strong oxidizing agent. Oh, and this one, wrong color. It is orange to start. Doesn't really matter though. Okay, so we've got this concentration. Now we can find out the concentration of our reducing agent. So, as it says up here, what is the concentration of the tin 2 chloride solution? So in this one, we're titrating tin 2 chloride or tin 2 plus as our reducing agent. And we're reacting it with acidified dichromate. So our half reactions are acidified dichromate, same one as before, Cr2O72 minus, reacting with 14H plus and 6 electrons to give 2 Cr3 plus and 7 waters. Okay, there's reaction number 1. Strong oxidizing agent reacting with our new strong reducing agent, which is tin 2 plus. If you go look it up on the table of relative strengths in the reducing agent column, tin 2 plus is not jumping out at me. Why not? Why not? Tin 2 plus should be okay. I'm not seeing it, but that's okay because I can build it myself. One more quick scan. Oh, there it is. Tin 2 plus goes to tin 4 plus. Okay. Tin 2 plus goes to tin 4 plus and 2 electrons. 6 gained, 2 lost. We got to make them equal, times everything by 3. Okay. Now we can add these up. 1 dichromate reacts with 3 tin 2 plus to give 3 tin 4 plus, 2 chromium 3 plus, and 7 water. If I was in a big rush, this is really what I need. This ratio, 1 dichromate for every 3 tin. So now we can do our stoichiometry. We have our balanced redox reaction, 6 gained, 6 lost. Okay, so now we're looking for the concentration of tin 2 plus. Start with the volume and concentration that we know. So we have the concentration of the strong oxidizing agent, and we have its volume from the table because we're titrating with dichromate. So these are all the volumes of dichromate from here. So our first one started at 11.8 and finished at 0.3. So that is 11.5. Our next one is 11.1, 11.0, and 11.1. So 11.1 plus 11.0 plus 11.1 gives us 11.06 repeating. So I'll carry all those digits through in my intermediate calculations. So concentration times volume for our strong oxidizing agent, the dichromate. So 7.78, I'm carrying all my digits through. Moles per liter of dichromate times its volume, 0.6 repeating. Okay, so there's my moles of dichromate, moles per liter times liters or milliliters. Okay, gives me my moles or millimoles. Now I'm interested in the tin 2 plus, so here's where my balanced equation comes in. 3 tin 2 plus for every 1 dichromate. Putting dichromate on the bottom this time because we want to cancel those out. We're looking for the tin 2 plus. Okay, so right now I have the moles of tin 2 plus, but I need per liter. So 1 over, and what is my volume of tin 2 plus? It's right here. Let's color code it. 10 milliliters of tin 2 plus reacted. Okay, cancel out. The milliliters cancel, and we are left with moles per liter of tin 2 plus. Plug all that into your calculator, and I believe you get this answer. 0.0259 moles per liter of tin 2 plus. Oh, big sigh. So you can see these problems take a lot of work. You have to understand titrations. You have to be able to do the redox to get the balanced chemical equation because we're after that molar ratio, and then you have to do the stoich. So there's really three things going on, which is why we save these till the last day of the chapter when the light is at the end of the tunnel. We just extended the tunnel a little bit. Oh no. Hang in there. A couple more and you guys will be good. So what I'm going to suggest now is that you try this first one on your own. So we are looking for the concentration of potassium permanganate. So we've got a table, and the title of the table gives us valuable information. We have acidic, so H+, tin 2 chloride, and permanganate. So tin 2+, permanganate, and because it's acidic, we've got that H+. So there's your strong oxidizing agent. The tin 2+ will be our reducing agent. I want you to come up with a balanced redox reaction. And then if you're feeling super confident, you can try the stoichiometry for this one as well. MnO4 minus and our tin 2+. This is our standard. We know its concentration. This is the one where we don't know its concentration. Unknown. So this is what we're trying to figure out. Holy smokes, is that ever messy? Ugh. Okay, see if you guys can do this one on your own. And if you can, awesome. You can pause the video here. Try this guy. It's in your study guide on page 214, sorry. Okay, and then come back to the video and see how you did. Okay, so I have my two half reactions, my strongest oxidizing agent, my strongest reducing agent. Here's my balanced redox reaction. Let's switch colors here. And here's what I know. Okay, so we're looking for the concentration of MnO4 minus. Again, start with what you have. We always are going to have concentration and volume of one of the two chemicals. So I'm looking for the moles, so I always put the moles on top. There's my moles per liter of tin 2+ times its volume. Weak students will put this volume in here instead. They don't pay attention to the volumes, which one belongs with which. So sometimes I say to students, if you're really weak, you can put moles of tin 2+ per liter of tin 2+ times 10 milliliters of tin 2+, and that just helps you to keep track of those volumes. That's optional. Okay, so now I've got my moles of tin 2+, and I want to convert it to permanganate. So I need my balanced equation. There's my tin 2+, and there's my permanganate. So the one we're looking for on top, the one we want to cancel out on the bottom. Okay, those are gone. And now I have my moles of permanganate, and I want the moles per liter. Here's my liters of permanganate. So it goes on the bottom, 16.8 milliliters of permanganate. The milliliters cancel out. Those tin 2+s are gone, and I am left with moles per liter of permanganate. And when you plug all that in, you should get this answer, 1.19 times 10 to the minus 2 moles per liter of permanganate. So that was step one, figuring out the concentration of the strong oxidizing agent. And then you could go on and do step two, where you figure out the concentration of the reducing agent using this value now that we know it. Okay. So I think, yeah, it's our last one. So I have one more problem for you guys to try, and you can try this one completely on your own. You have this in your data book or in your study guide as well. So if you want to pause the video here, see if you can determine the concentration of tin 2+ given this information. So just do it all on your own and then check back to see how you did. I will have the solution for you right after this. Okay, I'm going to do this one quick. So we are using acidified permanganate. Five electrons, 8H plus, goes to Mn2 plus and 4 water. Skip states just to speed along. Tin 2 plus goes to tin 4 plus and 2 electrons as our reducing agent. Common multiple is 10, so everything in here is doubled. 8 becomes 16, 2 of those, 8 of those. Everything here is times by 5 to get our 10. Okay, 10 electrons cancel out. 2 MnO4 minus, 5 tin 2 plus, 16 acidic ions, 5 tin 4 plus, 2 Mn2 plus, and 8 waters. Okay, so there is our balanced redox reaction. Now to do the stoich, we are looking for concentration of tin 2 plus. So we have a known concentration of dichromate, 0.0832 moles per liter of permanganate times its volume, and average volume of those is 12.4 mil. Goes on top so that the liters would cancel out. So that's moles of permanganate. For my balanced equation, we're looking for the tin 2 plus. 5 tin 2 plus react for every 2 MnO4 minus. And then our last step is that's moles of tin 2 plus, but we want moles per liter, and it's 10 milliliters of tin 2 plus. Okay, so concentration, moles per liter of tin 2 plus. And you plug it in, you should get 0.258 moles per liter. And if you do, hip, hip, hooray. Super happy. And these are your questions to practice. They're from the textbook. You can get the answers from the textbook as well on those. Hopefully you're good to go on that. It's our last topic for chapter 13. And again, send me questions if you've got them, and I will hopefully help you with that. Okay, take care, everybody.